So I just want to give a brief disclaimers that by trade I'm a logician, in particular a model theorist, and I sort of fell into this field by accident because a lot of the combinatorial quantities that appear in machine learning are also very important in model theory, and so I'll try to I won't get too much into the details, but I'll try and give you some sort of sense of the perspective that that I approach these problems with, and sort of some of the connections that come out of that. Okay. So first, let me just remind you all what the what sort of setting we're dealing in. So we have two set systems, C and H, on a set X, so just two collections of subsets of X, which may be finite or infinite. And in query learning, the learner is trying to identify a target set in C using membership queries and equivalence queries from H. So in an equivalence query, we submit a hypothesis from the hypothesis class H. And so success in this setting means submitting the target set as an equivalence query. So if we do so, we win, and otherwise we get a counterexample from the symmetric difference. So some element that tells us why our guess is different from the target set. For most of what I'll talk about, we're assuming a worst case scenario, which we can think of as where the counterexamples are being chosen adversarially, but there are also settings where the counterexample can be chosen randomly, and I'll mention that briefly later. And then a membership query, if we want to know whether or not a certain element X is in the target set, we can ask about that. And so our goal is to just establish a worst case number of queries to learn any possible target set from the concept class C. And we're just bounding the number of queries, equivalence queries or membership queries, doesn't matter. And so if there's a uniform upper bound on the number of queries we need to use, that will be the learning complexity. That will be this LC EQ plus MQ. And if we could possibly need arbitrarily many queries, we'll say that the learning complexity is infinite, or that that the class is not learnable. So there are a couple of basic questions that we're thinking about here. Given a class C, is C learnable at all? If so, what hypothesis class works? And we can also talk about efficient learning if we're given a collection of finite classes, or actually really given any collection of classes which are indexed by n. When can we learn in polynomially many queries, in here polynomial in n? So these are the basic questions that we're thinking about. And so okay, so let's talk about some parameters that are useful here. The first is Littlestone dimension, and then we'll just remind you briefly what Littlestone dimension is. So we have this binary element tree. So here, all of the A's are elements from the base set X, and all of the C's are sets from the concept class curly C. And in this tree, a leaf will be properly labeled when the path that we take through the tree determines the membership of the elements along the path on the way to the leaf. So in this particular case, if we go right, we want the element to be in the set, and if we go left, we want the element not to be in the set. So for C101, and I hope you can see the colors all right, we go right from a null, so we want a null to be in there. We go left from A1, so we want A1 not to be in there, and we go right from A10, so we want A10 to be in there. And so if C101 satisfies this, then it's properly labeled, and we don't care what C101 thinks about any of the other elements in the tree, which may be repeated but don't need to be. And so the Littlestone dimension of our concept class C is simply the maximum depth of such a tree where every leaf can be properly labeled from the concept class. And the first thing we want to recognize is that the concept class has to have finite Littlestone dimension in order to be learnable. If not, what happens if our concept class is infinite Littlestone dimension, then basically no matter what we do, no matter what equivalence query we submit or what membership query we submit, there will always be a way for an adversarial teacher to give us an answer such that the Littlestone dimension of the remaining possible concepts is still infinite. What are we really trying to do here? We're trying to identify the target set. Identifying the target set we can really think of as reducing the Littlestone dimension of the class of remaining possible concepts to 0. A class with Littlestone dimension 0 just consists of a single set. And so if we reduce Littlestone dimension to 0, then we've identified the set. I won't say too much more about that, but that's a little bit of a rough sketch of why finite Littlestone dimension is necessary. But it's not sufficient, and so we also need to talk about consistency dimension. So as Steve said, this is well. Let me give my formulation of it, well, sorry, I should say this is not my formulation of it. This is consistency dimension has been around before, but the formulation that I'll use. So a subset, A of X, and we'll think of a subset, we'll identify a subset with its characteristic function, is n consistent if every restriction of A of size n has an extension of C. So in other words, it's n consistent if whenever I look at the trace of A on n elements, I can find some element, some set in the concept class that has the same trace on these n elements. And I can do so for all size n subsets. And so the consistency dimension is going to be the least n that says if I have a set that's n consistent with C, then this set itself is in H, is in my hypothesis class. So this is a property of both the base concept class C and the hypothesis class H. So this is sort of we sort of want to think of it as how well can H simulate locally what's going on in C. And so I should say that consistency dimension is lower consistency dimension indicates a larger or a richer H. So for example, consistency dimension 1 would say that wherever I can basically consistency dimension 1 means that H would have to be the full power set. And let me just give a brief remark about comparing the formulation of dual Helly number that Steve talked about. When I talk about consistency dimension, this is slightly more restrictive, because when I'm thinking about a subset A of X, I'm thinking about it as a total function from X to 0, 1. And the formulation of dual Helly number that Steve gave, since it looks at subsets of basically X cross 0, 1, that formulation allows for the possibility that you're agnostic about some elements. And that's strong consistency dimension, which I'll also mention later. Okay, but what's going on here? The consistency dimension is a measure of how well we can locally approximate things. And the key idea here is that if A is n-consistent with our concept class, but it's not an H, then it's possible for an adversarial teacher to simulate this set for at least n queries. And so the only way for us to sort of disprove that it's not A is either to exhaust all of those n queries or submit A itself. But if A is not in the hypothesis set, then we can't submit it. Okay, let me give an example that will hopefully make this more straightforward. Take X to be an infinite set and consider just the collection of singletons. This class is not learnable with queries just from itself. You can think of this as just saying, okay, I'm holding a natural number behind my back. Can you guess what it is? And you might guess, okay, well, is it 7? And is it the singleton set 7? And I provide a counterexample. The counterexample will be, that I'll provide will be 7. So, which all I'm doing is I'm saying that 7 is not in the target set. Well, what about 53? Is the singleton set 53? And I'll say, well, no, 53 isn't in the target set. So you're basically just, you're just basically guessing natural numbers, which isn't, you're not gonna, that's not gonna do you any good. And so it's only gonna be learnable if you have the empty set available as a query. Because if you have the empty set available, you can query that. I now have to give you a counterexample. How is the empty set different from the set that I'm thinking of? Well, if I'm thinking of the set, the singleton set 20, the only counterexample that I can give you back is 20. And now you know that it's the single set 20, and you can submit that and you win. And on the other hand, what's happening when you're, if you're just submitting natural numbers, when I'm just saying no to everything, you can think of that as I, the adversarial teacher, am just simulating the empty set. And I can do so for arbitrarily many queries in this case. And keep in mind, all of this happens in a very simple setting, right? This is a very simple set system. It just has Littlestone dimension 1. So we need to talk about both the target concept class itself and the hypothesis class. And Littlestone dimension and consistency dimension are how we do that. or at least how I'm doing. Okay, so when is this possible? I've sort of tried to set this up. If both Littlestone dimension and the consistency dimension are finite, then we can learn in a roughly C times D mini queries, where C is the consistency dimension and D is the Littlestone dimension. And if either of these quantities are infinite, then the Littlestone dimension, if either of these quantities are infinite, then the learning complexity is infinite. And so,
Hunter, sorry, can you give an example where the Littlestone is infinite while the consistency is dimension is finite?
Sure. Take the collection. Take the collection of thresholds. So just one-sided intervals on, say, the real line. So this will be just all intervals of the set from x to infinity on the real line. This will have finite consistency dimension. And here I'm taking both the hypothesis class and the concept class to be the same thing. So this will have finite consistency dimension because if something isn't an interval of this type, then we'll be able to find a point x that is in the set and a point y which is greater but not in the set. So that'll give that will have finite consistency dimension.
So consistency dimension would be what, 2 or 1?
Yes, 2.
Okay.
Yeah.
Okay. And the infinite Littlestone dimension, that I understand. Yes.
Yeah. Yeah.
Thank
you. Yeah, because and then, you know, in that case, learning sort of becomes, can you nail down an endpoint in a dense linear order? And we won't be able to do that. Okay. And so, as I sort of said earlier, I'm using Littlestone dimension here as a measure of the complexity of the remaining possible concepts. And so I'm trying to reduce this class, the Littlestone dimension of this class, to 0. And so the role of consistency dimension had already been known, but what I think is novel about this bound is it incorporates Littlestone dimension rather than the log of the size of the concept. So the previous bounds were something like consistency dimension times the log of the size of the concept class. And so here we replace the log with Littlestone dimension, and this actually allows us to look at cases where we have an infinite concept class. So these bounds apply whether or not your class is finite. And we can also use this to talk about efficient learning. So if we have a family of classes indexed by n, can we use polynomial and n mini queries? So this is just the same bound from the previous slide, but the important thing to note is that, right, this bound is basically C times D. So it's polynomial and Littlestone dimension and consistency dimension. And we can also find appropriate lower bounds. So consistency dimension itself is a lower bound, and a concept times Littlestone dimension is also a lower bound. So we get polynomial bounds on either end. And so we can characterize efficient learnability by, we just need to have that consistency dimension and Littlestone dimension grow at most polynomially. And so we can use these techniques to reprove efficient learnability in several cases. So I think I have time. So let me talk about an example. So let me talk about learning regular languages. So and we'll talk about this in the language of using deterministic finite automata. And so our classes will be DFAN will say this is the class of regular languages accepted by a DFA with at most n nodes. So a classic result says that we can learn in O of m times n squared many queries, where m is the length of the longest string that we encounter during our course of learning. So we give a new proof of learning, which doesn't mention the length of the string at all. So using our techniques, what do? We need to give bounds on Littlestone dimension and consistency dimension. Littlestone dimension here is not especially interesting. We just use a straightforward counting argument. Consistency dimension is a little bit more subtle. So given a collection of binary strings, we'll say that X and Y are related. So we're thinking of C as our language. We'll say that two finite strings are related if and only if for any suffix, X with this suffix is in the set if and only if Y with this suffix is also in this set. And the Myhill-Néraud theorem says that so this is an equivalence relation. And the Myhill-Néraud theorem just says that this C will be a regular language that's accepted by a DFA with at most n nodes, if and only if this relation has at most n classes. Well, sort of the way that I've defined it, if we have at least n+1 classes, then I can exhibit this. Using 2 times n+1 choose too many queries. So for each pair of n+1 many classes, I choose 2 strings to show that they're in different classes. So what is this consistency dimension saying? It's saying that anything that has n+1 many classes, I can show that it has at least n+1 many classes using 2 times n+1 choose 2 many examples. And so that will exclude anything that doesn't fit in DFA, and that will give us a reason why it's not in DFA. So that gives us the consistency dimension. And then so putting the 2 results together, we get an upper bound on the number of queries that we need. So this is just the n squared from the consistency dimension times n log n from Littlestone dimension.
Do you have a lower bound for this corollary for the type?
I mean, the lower bounds that we get are just Littlestone dimension and consistency dimension.
No,
so yes.
For the consistency dimension of DFA,
Oh.
is it n squared, or can it be much smaller?
I don't know off the top of my head.
Basically, the question is, I give you a regular language and they give you string not in the regular language that is not accepted. Then the question is what is the largest substring which witnesses it, right?
Yeah. Okay. I don't. Okay. I'll be careful, but I think that. Okay, I haven't written this down anywhere, but I'm guessing that you can't improve that because I mean, because the Myhill-Nerode theorem is an if and only if. So it says that the obstruction to being a regular language on n nodes is precisely that you have n+1 many classes. I guess if I guess an improvement would be you could possibly, maybe you could improve it if you could show that you can find examples if you can use for one pair, if you can use if you use one pair of strings to show that they belong to different classes, can you use one of the strings in another class? I don't know. So yeah, I'll sort of stop this wild speculation, but my guess is you can't improve it that much.
Thank you.
Okay. 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 So as I think I've mentioned, consistency dimension was already known to play a role in query learning, and Littlestone dimension hadn't been used as much. You can sort of use it in the sense that if you look at the case where your hypothesis class is the full power set, then equivalence query learning is not really any different from online learning. And of course, Littlestone dimension characterizes the online learning. But I just sort of want to try and sell sort of the power of Littlestone dimension. So of course, one of the things that it does for us here is it allows us to move from finite classes to infinite classes. If that's sort of what you want to do. And the other thing is that the divide between finite Littlestone dimension and infinite Littlestone dimension is very powerful. So it provides sort of the language to talk about online learning. It also has a lot of other interesting things going on. For instance, a set system will have finite Littlestone dimension if and only if there is a finite bound on the size of a class of thresholds that it can simulate. And I won't get too much into the details about what I mean by that by simulate here. But these sort of infinite binary trees has sort of something to do with simulating an order. So this was used, for example, to use Littlestone dimension to characterize approximate private path learning. And so one of the techniques that was used there is that intervals are not privately pack learnable. And so if you have infinite Littlestone dimension, then you can do this sort of simulation business. And I won't get into those details. The other thing is, and this is sort of where how I got into this, is that Littlestone dimension also plays a very large role in model theory. So model theory is a branch of mathematical logic that looks at properties of mathematical structures and their definable sets. And Littlestone dimension can be used to characterize a certain class of structures called the stable structures, which are very well behaved. So in this, so for example, the class of algebraically closed fields belongs to this family. And so in these structures, every set system that you could reasonably generate will have finite Littlestone dimension. And finite Littlestone dimension also characterizes this. So in this sort of model theoretic world, such families are very well behaved, and there's been a lot of machinery that's been built up around there. And I'll also mention that there are more ties between machine learning and model theory by way of combinatorics than just this. For instance, VC dimension also plays a large role. Finite VC dimension can be used to classify another class of structures that is also quite well behaved, called the MIPT, or dependent theories. And so, and of course, we know about the relationship between finite VC dimension and pack learning, for example. And consistency dimension also appears in model theory in its own way, in a little bit more subtle thing that I won't mention too much. So let me just say that I think it's very interesting that a lot of the combinatorial tools that we talk about have a lot of power in other fields of mathematics so hopefully that can be used to create a dialogue between the two. Certainly the dialogue between VC dimension and MIPT theories and some machine learning things around that make use of VC dimension has been very interesting and very fruitful in my opinion. Okay, but let me not get too much into that. So let me mention a couple of questions. So what about the case where we only look at equivalence queries? And this sort of gets back to the Helly number and what Steve mentioned as strong consistency dimension. So we can characterize learnability using consistency dimension and Littlestone dimension, but we don't get a characterization of efficient learnability, as the upper bound that we get this is exponential. So, and consistency dimension for one reason or another doesn't seem to be the right parameter. And as far as potential alternatives, this strong consistency dimension does seem to be a reasonable alternative, although we don't have results yet. We don't have efficiency results, the sort of efficiency results that I would like to have. But there are already known bounds that use strong consistency dimension in the case where we're just using equivalence queries. And as another example where I think Littlestone dimension is particularly useful is, or maybe at least interesting, is the setting where we look at random counterexamples. So there was a paper a few years ago showing that in this setting we can you get a bound that is basically log the size of the concept class, and we show that if you like, you can replace that log by 2 times the Littlestone dimension. And the power of random counterexamples is really that you don't have to expand the hypothesis class at all. And so in this case, we show that the Littlestone dimension can still be a useful parameter. Let me just, however, our results here still assume that the class is finite. So we can't jump to to infinite classes the same way that we've done for the setting that I was talking about for most of this. But I think it's an interesting question about whether or not it can. Although a lot of the it seems like a lot of the details get a little bit uglier, but
okay, I think that this is the time to wrap up, because
yes, well, that's all I have. So
okay, thank you very much, Shante, for the very interesting talk. Any more questions?
So this last question that you mentioned, and the last thing that you mentioned, is it in any paper of yours?
So the 2 times Littlestone dimension is in a preprint, which is on the archive, and there's nothing out yet about infinite classes yet. That's something that we're still working on.
Okay, and another question I had is, so you get this upper bound, which is basically a product of this 2 dimensions, and the lower bound, which is like the maximum of the 2 dimensions, right?
Yes.
So is there any hope of bridging the gap, meaning like proving the corresponding lower bound, or what would you expect to be the right behavior?
That's a good question. I don't know. I think certainly there are I think my guess is that my guess is that you can't in general tighten this. I know that there are examples where consistency dimension is a lower bound is tight, can be achieved. The Littlestone dimension as the lower bound is a little bit tricky because just because of just sort of some of the weird constructions of how Littlestone dimension behaves if you split up two concept classes, if you split a concept class into two. I think if there's an improvement, it would probably be in the upper bound, but I also I don't think I have a general example that shows that it's uniformly tight, but my guess is that it's probably pretty close. But of course, that's you know, of course, how things behave in practice in specific problems. You know, who knows.